Alright, in this section, we're going to study something called the normal distribution. It looks like a bell curve, and I wanted to start by motivating it a little bit. In our formulas that we have, you see that the n factorial needs to be calculated. It turns out that those numbers get very large very quickly. Let me show you what I mean by going to our calculator and trying to evaluate not even a large number factorially. So on your calculator, type 70, go to math, go to PRB, and then of course choose number 4 and enter. Do you see what it says? Overflow. It won't do it. Now, let me come back to it. Go to. I'm going to change this number to 69. And you can see that E98 means that the total length of this number is 99 digits long. So it's a huge number. So 70 factorial was too much for this calculator to take. Now, I happen to have a calculator that will do this kind of stuff. Let me go to 70 and see if I can find my factorial here. I think it's in this key. Yeah, there it is. Enter, and then enter again. And you can see what happens is the E100 is the limit of the TI calculator, but the Hewlett-Packard calculator can do this all day long. In fact, I was able to get it to print out all of the digits, not like this, but actually print out all the digits. There is a way to do that. So the n factorial is too big quickly. Imagine not being able to ever study subjects that have 70 or more things in them just because you're limited by your calculator, or computers will be limited too. These numbers just get too big, they're unwieldy, and so we have ways of dealing with that, but it's a totally different method than what you're used to. So what we're going to do is this. Flip a coin and count the heads. So let's try this first. Let's flip a coin 2 times. We know that the outcomes look like this. We could have 2 heads. We could have a heads, tails, or the tails could have come first and then a heads, or a tails, tails. Each of these is equally likely to happen, so each of these has a probability of 1/4. Now what I want to do is I want to draw pictures of this to show you how this progresses. So the number of heads will be down here, so let's call this the number of heads. And you can see that I can either have 0 heads, I could have 1 or 2 heads. Now what are the probabilities? I'm going to label them as 0.25. It'll probably be easier to do decimals here, and 0.5. So having 0 heads means it's 2 tails, and there's only one place out of 4 where that happens. So the probability of 0 heads is 0.25. And while I'm at it, the probability of 2 heads is the same as the probability of 0 tails. It's going to be the exact same probability. And then the 0.5 here, when 1 heads, there's 2 spots that have 1 heads. So that has a probability of 0.25 plus 0.25. And here's a picture that we have. I'm going to draw something. I'm just going to kind of connect these with curves. Not a great looking curve, but I just want you to see the beginning of something. Now let's flip a coin 3 times. We know that we have 2 to the third power number of outcomes. That's 8. So let's start here. We'll start with 3 heads, and then look at all the possibilities with 2 heads. And then look at all the possibilities with 1 heads. And then finally, no heads. Each of these has the probability of 1/8. So every single one of these things has the probability of 1/8, which is 0.125. You don't have to really follow this. I just want you to see how the picture is going to progress as we go on and on. So now I can have 0 heads, I can have 1 heads, I can have 2 heads, or I can have 3 heads. So once again, down here is the number of heads. And I probably should have put along here, this is the probability. Alright, so these go in increments of 0.125. And let's take a look at our numbers. The probability of 0 heads, let me go over here, that's 3 tails, of course. That's only 1/8. That only occurs 1 out of 8 times, so its probability is 0.125. I gotta be careful with that. Got my dot. Now, you can use symmetry to go over here and say the probability of 3 heads is the same, because that's really the probability of 0 tails. So there's a lot of symmetry that you can use here. Now the probability of 1 heads, let's take a look at all the places where there's 1 heads. Here's 1, here's 2, and here's 3. And I think you'll find out there's only 3 out of them. 3 out of 8 is 0.375. So let me go ahead and put that a dot there. And you can do it for 2 heads also, because that's the same as 1 tail. And then I'm drawing this picture in the hopes that you'll start to see it grow. The middle there, since we have an even number of numbers, the middle doesn't have a dot at the top of it. And as if I don't need to do more, flip a coin 4 times. So this time, now the size of the sample space is 2 to the 4th, which is 16. Let's take a look at my possible outcomes. I can have 4 heads. I can have 3 heads and a tail. So I'm going to list here all the ways of having 3 heads. And then let's take a look at all the way of having 2 heads. And then we can do TH, TH, do T, T, H, H. Now we know we need 16 of these. Now let me do all the ways that we can have exactly 1 heads. So that can look something like this. And then we can have tails, heads, tails, tails. Then we can have tails, tails, heads, tails. Tails, 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 heads. Those are all the ways that we can have 1 heads. And then how many ways can we have 0 heads? Well, that's just all tails. Now, I know I'm going to be good if I count this up and I have 16. These can be slippery, so be careful. Let me see. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So where is that 16th one? All right, I found it. I don't think I did this one. I don't think I did H, T, T, H. Let me show you something, how you can check yourself a little bit. I was trying to find out where my 16th one went, so I was looking at these twos because I think I did them all. If you look, we have 4 letters and we have 2 H's and 2 T's. So the number of them that we should have is 4 factorial over 2 factorial times 2 factorial. 4 letters, H is repeated twice and T is repeated twice. Well, the top is 24 and the bottom is 4, so that equals 6. So if you look at my guys, there's 1, there's 2, there's 3, there's 4, there's 5. I could see that I was missing this guy right here, this HTTH. No big deal. All I care about is that I got all 16 of them, and I want to draw a picture. I'm going to probably at some point dispense with lots of details because I hope you see the shape of the picture is starting to take 0 heads, 1 heads, 2 heads, 3 heads, or 4 heads. This is as many heads as you can do. Number of heads. And of course, here is the probability. Now, once again, here everything has a probability of 1 over 16 of happening. And 1 over 16 is 0.0625. So let's start with 0 heads. That would be 4 tails. Its probability is going to be very small. What I'm going to do is 0.125 like I had before. I don't know if I need to go more than that on these. But 1 heads is 0.625. It's 1/2 of that actually. And don't forget, whenever you do that one, you can come over here and repeat it because tails acts the same way. 4 tails is 0 heads and 4 heads is 0 tails. Now let me move on to 1. How many of these did we have? 1. We had 1, 2, 3, 4. So 4 out of 16 is 0.25. I can put a dot there, and then I can also do it for 3 because of symmetry. And then finally, how many heads? 2 heads. That's 6 out of 16, which is 3 out of 8. That's 0.375, so it has a dot right in the middle. And I'm going to draw this picture and see if you can see it happening. Now, in our textbook, we go a little farther than that, so let me grab a picture out of there. Well, as we flip the coins more and more, here's what's going to happen to us. It's going to take shape, and it's going to take the shape of a bell curve, something like this. You may not know this, but right under the top point is the mean. So that's always the tippy top of this graph is the mean. And every time, if you were to go and find the shading part of this, you will find that that equals 1 square unit. And I should probably draw a 1 that looks reasonable. This is 1 square unit. Always, no matter how many times you flip the coin, if you do this under the curve, you're going to get 1. So really, after you flip the coin, say, I don't know how many times, something like an infinite number of times, the curve actually becomes curvy for sure. And through calculus, we're able to generate this curve and always get it so that the mean is in the center. Now, what we're going to study is the normal distribution. It's easiest to look at the graph to see what it does. And I'm going to draw one here on our calculator to show you what it looks like. I'm not going to draw the actual one, but let me turn it on and go into y equals, and I'm going to clear this. Now, this is not for you to do. This is not, I don't expect you to do this part, but I do want you to see the shape of the curve as drawn. So what I need is an exponential, and you may or may not know of this creature. This is e. I'm going to put a negative x squared. You can enter your way out of that. You do something called a zoom 6, and it puts it like in a standard viewing screen. Now you can't really see stuff that well, so if you want, change your window, and I'm going to go probably from -3 to 3, and the Y's are very small, so I'm going to go -0.25 to, let's do 1. And then if you hit graph now, it'll look a lot better. You see there's our curve right there. So there's our normal distribution curve. The area inside of this, as I mentioned, is 1 square unit. The center here is the origin at 0. I know it's not at x with a bar over it, it's not at the mean, but this creature, if we study this thing, what we'll be able to do is adapt it to our particular situations where the mean is not 0, and we're also going to talk about the standard deviation a little bit. So when I draw a curve, I'm just going to draw something like this, usually. Like so. And what they do, for some reason, here's what's called the x-axis, or you know what they do? They don't even call it the x-axis. They refer to this as the z-axis. They give it its own name. Its center is at 0, and the area under there is at 1. The reason I'm drawing this is because I want you to see how my curve looks versus theirs. Mine looks bad. Theirs looks really good. But I'm just going to draw this creature like this from now on. And there's more details too. Notice the way it tends at the ends like this. If I were to have drawn it correctly, it does this. It actually doesn't touch this line, the z-axis, if you will. It doesn't touch it. It gets closer and closer to it, and as close as you can imagine, but it never actually touches it. The same is in that direction as well. So once again, let me put 0 here. And there's even more. If you look, there's a point. Follow the curve, the cursor if you can. There's a point here. I'm going to make it here. I think I'm going to put it here. Where if you look at this graph, it looks like it's going downward, but it's bowed inward. We call this concave down. But after this point right here, it starts to shift and become concave up. The same thing here. We have a point where it's concave down, but then after that point, it's concave up. This happens to occur at 1, and this happens to occur at -1. And in fact, what we have here is that the mean equals 0, and the standard deviation equals 1. Now the way we're going to work our system looks like this. We're going to study this curve and know all about it. We even have a table of values for it. But what's going to happen in our problems is this. Instead, you're going to be given a mean that is not 0, and the standard deviation, we don't know what it is, but I do know that it's 1 standard deviation over from the mean on both sides. So on there, it's x bar minus s. So these points where you have where you add standard deviations on like that, they're important. Down here we have x bar minus 2s, and all the way over here, let me put myself an arrow here, we have x bar plus 2s. And so what you can see is my graph is going to lose credibility if I keep going here. Let me grab one from the book and sort of explain it better. Okay, what I've done is drawn the picture, or pulled a picture from the textbook. And you can see that this center point is the mean, that's x bar. And then as we move over, one standard deviation to the right, we capture 34% of the data. Or instead of 34%, if you prefer, this is 0.34. You may not be able to see some of these. And down here is 0.135. 0.135. It just depends if you like decimals or the percentages. You'll find that using decimals will be easier for your calculator. But our book goes all the way out to x plus 3s, and you can see the area that's left here, even though this thing doesn't touch this x-axis, the area that's in there is only 0.15%. So you can see that in the outerest regions, there's almost no data. Now, a lot of things follow curves like this, especially student grades on, I think, standardized exams follow a curve like this. And it turns out there's a lot of things that do follow a curve like this, but they don't look like it from the outset. And the binomial curve, or the binomial distribution, if I flip that coin more and more times, say getting close to an infinite number of times, and I drew this for the number of heads, it would be a nice smooth curve like this. And in what we call in calculus, in the limit, we would get this curve. So we want to, right now, just know this sort of a breakdown, because this will be important to us as we do some of the problems. Remember, underneath the entire graph itself, I don't have it listed in this picture, but underneath the entire graph, always remember this. The probability underneath of the entire graph is 1. That's because the probability of the entire sample space is always 1. Remember, no matter what, probabilities are always less than or equal to 1 and always greater than or equal to 0. So when you talk about the area under the entire curve, I'm talking about the entire sample space, the data for the entire sample space, and that should equal out to 1 square unit. Some other things about this curve that I want you to know are the following. Let me grab another one from the book. Here is yet another picture of the curve. There's the mean right there. There's our x bar. And on each side of the curve, you have 50% of the data. Together, they add up to 100% of the data. Not only that, there's an incredible symmetry. Whatever happens, say if I pick a spot here, I don't really care. I can go across the graph, and to the exact same place here, I have a dot there as well. So this is a mirror image about this mean. Here I've brought the picture back again just to show you something. We'll adapt it to our situations like this. Suppose I have an x bar of 6.3 and an s equals 1.2. The picture that I would draw to accompany that information looks like this. I'm always going to draw really the same bell curve no matter what. Even if it looks bad, that's not that big of a deal. I'm going to put down here, this will be the 6.3, that's the mean. And then put your standard deviations in there. There's 1, 2, and try to sneak in 3 of them. 1, 2, 3. I want to make it symmetric as well. So when I do that, these standard deviations are 1.2 over. So I go to 7.5, 8.7, and 9.9. You can make these little lines in here if you want to sort of break up the data like that. And my curve does not look very symmetric by the way I drew it, but hopefully you can look past that. Now when I go to the left, I'm going to subtract increments of 1.2. So I'll have 5.1, 3.9, 2.7. And if you want, here we have 34%, 34%, 13.5%, 13.5%. Got to do this for these ones, they're so small. 2.35%, 2.35%, and then finally this teeny little piece at the end, 0.15%. Same over here, 0.15%. So that's how we'll adapt it for our own case. We'll be able to take a collection of data and compute the standard deviation and the mean, and then we'll be able to put it to the curve. So to get a better idea of what we're doing, we'll have problems where we will shade in portions of this graph, and we'll want the various percentages. Or you can put it as decimals. So what you need to do is look at any graph like this. Maybe it's even better to have this one here. If we're looking at these three, let's have these numbers in those spots. So in this spot here is 13.5%, 2.35%, 0.15%. So the area of the blue is the entire area. You're going to have 13.5% plus 2.35% plus 0.15%. What does that give us? Well, luckily these all add up to a whole number, and I get 16%. So the entire shaded area is 16% is blue. Well, that doesn't hurt then to figure out these. Now, if I wanted to figure out what the yellow ones are, I'm not going to do the individual amounts like this. All I'm going to do for the yellow is do 1 minus that. Yellow area equals 1 minus 16%, which is 84%. So this yellow area out here is 84%. And so you'll be able to answer questions like that. Notice that I did not label individually these things because by knowing this chunk out here, since it goes all the way out to infinity, I know that the whole thing is 100%, so I just subtracted this amount from 100%. Here's another one. Let's take a look. Down here, we have 2.35%, and that little piece at the end, 0.15%. Ooh, look at this, sneaky. Sneaky, sneaky. Look at that. There's a blue area in here, too. That must be 0.15%. And so let's go ahead and get these areas. So the blue area equals, we're going to have to do 2.35% plus 0.15% plus 0.15%. And it looks like we have a total of 2.65% in the blue. So then the yellow area will equal 100 or 100%, or I could just use the number 1, minus 2.65%. That equals 97.35%. So this area here is 97.35%. All right, for these areas, what I'm going to do is this. What I get is, for the yellow here, I get 2.35%, and for that little piece at the end, I have 0.15%. So the yellow area equals 2 times that, because you also have that same quantity over here. So I've got these two pieces for my yellow. I'm going to do 2 times this. I'm using the symmetry of the 2.35% plus the 0.15%. That equals 2 times 2.50%, which is equal to 5%. So the area in the yellow is 5%. That means if I want the area in the blue, I'll subtract it from 100%. So the area of the blue is 95%. I don't know if you'll be able to see it in there, but there's 95% all in that spot. All right, the way we're going to attack these problems, here I grab one from the book. We're going to look at the average. Right here, there's an average of 12 dogs, so that'll be my mean. and a standard deviation of 3. So the 3 dogs, or just 3, that'll be my S. So let me write this down. X bar equals 12 and S equals 3. So we can draw a picture. The first thing you're going to want to do in any of these types of problems is draw a picture with that information in it. The bell curve can always look the same if you want. You don't need to do anything special for it. And then we're going to make sure that our mean is at 12. And then we're going to do standard deviation increments to the right and to the left. So let me get my minus 3 is 9. Then we have 6. And then we have 3. And then kind of make these little marks here so that you can remember the areas that are involved in each one of these. All right, now they have some of the problems here. What is the probability of having more than 18 dogs? So let me show you how this works. Let's do part A. I draw a picture again. For each of these, I draw a picture. You can draw it as tall or whatever you want. And here would be 12. Now we want more than 18. So here's 15, and then there's 18. So let's get the areas involved in these things. He wants the area of more than 18 dogs. So I'm going to do the probability of more than 18. So we're talking about this area inside of here. Remember, the area in this spot is 34%. The area in this spot here is 13.5%. The area of the entire half is equal to 50%. So let me add these two pieces together. So I'm going to have 34% plus 13.5%. That will equal a total of 47.5%. That means what's left over, I have to subtract it from 50%. So I'll do 50% minus 47.5%, which equals 2.5%. Or, I personally don't like writing my answer as a percent. I would write 0.025, like so. But that's just me. You can do what you want. Next, we want the probability of, what did it say? Between 12 and 15 dogs. So what you might want to do and get used to it is this. We actually want the probability that our X values are between 12 and 15. This is really mathematically how it looks. You always draw the picture once again. One picture for every problem. Oh, it looks really bad there, but I'll see what I can do with it. And let me go ahead and put my mean here. And they want between 12 and 15, so I don't have to do a lot here. I'm simply looking at this chunk, and we know that that is 34%. So this equals 0.34 or 34%, whatever you prefer. Finally, for this, we want the probability of less than 6 dogs or greater than, I want to make sure I get the number right, greater than 18 dogs. Let's draw once again a picture. That might be my best looking one yet. All right, I'll put my mean here, which was 12. And then we had 15. And then we had 18. Since we're talking about 18, I don't need to go any further than that. I have 9. I'll have 6, so I'll stop here. So I'm talking about this area here plus this area here. Now let's take a look at what we have in these chunks here. We know this is 34%. 34%. We know this is 13.5%. So stop right there. This whole side on the right is 50%. So since these two pieces add up to 47.5%, that means this is 2.5%. Well, I have a piece here, and I also have a piece here. So 2.5%. So the probability of this is going to be 2 times 2.5%, or just 5%.